So for Chapter 4, is a focus on non-parametric approaches, starting with describe the bootstrap historical simulation approach to estimating coherent risk measures. And so the idea here is we start with a data set of indexed returns. So again, think of this portfolio in 2 dimensions, right? The portfolio here goes down this column, and in this example, the portfolio consists of 4 assets. So that's the column vector. That's a column vector of positions in assets. Together constitutes the portfolio. And then over time, we're going to have returns, right? So we've got time as the dimension in this row, and the portfolio represented as a vector of assets in the column. The returns are what they are, and then we can index those returns off some baseline, and we have the matrix of returns. So in the bootstrap historical simulation, we're drawing random samples, but what we're doing is we're going back into the history and picking out a column vector. So maybe we simulate for the first day, we go back and use a random function to randomize and pick one of our column vectors. So for example, we pull from March 6th, the column vector, and our random sample determines which day we draw from. Having determined that, then we go pull the actual index returns for that day. So notice that's a column vector of index returns that actually happened on that historical day. And then we're saying, okay, we're going to assume or simulate that that's what happens today or tomorrow. And then that'll give us simulated prices. And then we go forward another day. Notice how it's looking like a Monte Carlo simulation. So it is a simulation. But when we go forward the next day, it's not based on some kind of engine like a geometric Brownian motion. Rather, to find out what it does from today to tomorrow, we go back, draw from our sample with replacement, random draw with replacement, and maybe we randomize and decide to pull from March 5th, that column vector of actual index returns. And we just apply those returns. So whatever happened on March 5th, we assume that happens on n+1. So those index returns will give us new values, simulated values. And then again, we do that for n+2. For the next day's behavior, simulation, we go back and pull from an actual history. And this will allow us to simulate going forward these values of the portfolio. So let me make an important point here about the correlation. This means that when we go back with a bootstrap simulation and we look at, for example, we decide to pull from March 6th or March 7th, and again, n+1 might pull from March 6th, and then we go to n+2, it might, because we're doing we're a random draw with replacement, we might go back and use March 6th again, just by virtue of random sampling. So we can repeat. Now, when we pull that vector here, notice any of these, I like to think of this as cross-sectional correlations. To the extent asset 1, 2, 3, and 4 had any correlations within that day, those do get picked up, right, in these index returns. So these cross-correlations, or what would just be called correlations, do get preserved or do get incorporated into our historical simulation model. However, what does not get incorporated, you'll notice, is when we go forward each day. Historically, 3.5 led to 3.6 led to 3.7. We would call that auto or serial correlation. Auto or serial correlation would be correlation across time. And now, if these assets were auto-correlated, notice because we're going back and randomly selecting each day, maybe with repeats, the autocorrelation is not being picked up in the historical simulation. So the summary point there is, this has the advantage of picking up these, what I would call cross-sectional correlations, or just correlations. Those do get incorporated in the model. However, it would not pick up autocorrelation or correlation across time. Describe historical simulation using non-parametric density estimation. Simple historical simulation only allows the VAR estimate at discrete confidence levels. Non-parametric density estimation treats data as if they were drawings from some unspecified or unknown empirical distribution function. A simple way to do this is to draw in straight lines connecting the midpoint to the top of each histogram bar. Although better in theory, this does not necessarily produce a much better estimate in practice. So then we have some, Dowd reviews some variations on that historical simulation approach, or the simple historical simulation approach. Because the simple historical simulation approach That's where we looked at an actual, even that GARP sample exam. We take the historical data and just sort it by the profit and loss, worst to best, each day. So if you think about it, that is an unweighted or equally weighted. We're treating each return with an equal weight. We can call it equally weighted or unweighted. It reminds me of in volatility, where we have the basic volatilities is implicitly unweighted or equally weighted. And then we improve on that by GARCH or exponentially weighted moving average by weighting more recent returns. Similarly, we can improve, in theory, on the historical simulation by moving away from equally weighting each of the days or unweighting them to variations on weighting, including age weighting, volatility weighting, correlation weighting, and filtered historical simulation. So in age weighting, this is identical to Linda Allen's truncated hybrid volatility, which is a hybrid of exponentially weighted moving average and historical simulation. So the weights here are in constant proportion at lambda. And then I have an example here. If n equals 10 and lambda equals 90%, the weight in the weight in the second period would be 90% times 10%. That's 90% times 10% divided by 1 minus 90% raised to the 10 equals 13.82%. And the ratio of these weights is in constant proportion lambda. The benefits, it's a simple historical simulation then becomes a special case where lambda equals 1 or we have zero decay. A suitable choice of lambda parameter can make the VAR estimates more responsive to large losses. This reduces the ghosting effect and is flexible to modify. In volatility weighting historical simulation, we weight the returns by relative volatility. So we have a ratio here of volatilities. It just serves as a weighting function on the return. This directly accounts for volatility changes, allows us to incorporate GARCH forecasts, can obtain VAR or expected shortfall estimates that can exceed the maximum loss in the actual data set. Right, we can see this can actually multiply or levering this up the return above 1, so we can actually get VAR estimates exceeding the actual loss. That's sort of interesting. The authors give empirical evidence to support the superiority of the volatility-weighted historical simulation. And then we can have correlation weighting. This approach is a major generalization because it gives a weighting system that takes into account correlations as well as volatilities. Filtered historical simulation, a semi-parametric bootstrap which aims to combine the benefits of historical simulation with the power and flexibility of conditional volatility models like GARCH. And then we have some summary advantages and disadvantages, that is, advantages of the historical simulation and some of its non-parametric flavors that we just looked at, like volatility adjusted. It's intuitive. It handles non-normal returns, skew or kurtosis. In theory, it handles any position type, including derivatives. Popular among risk practitioners, relatively easy to implement, no curse of dimensionality, uses readily available data, is easy to report and communicate the results, easy to generate confidence intervals, and it can be combined with parametric add-ons. So this historical simulation is not mutually exclusive with parametric approaches. And the disadvantages are, if a history is a quiet period, the VAR estimates will be too low, difficulty of handling in-sample shifts, can be dominated by extreme losses, most are subject to ghost effect, generally makes no allowance for plausible events that might occur but did not occur, and to an extent constrained by large losses in the dataset. Chapter 5, or just the appendix, is assigned to introduce copulas. And the main reason that we look at copulas is due to the drawback of correlation. So in really all of part 1 of the FRM and the econometric section and the correlation that we're used to seeing and denoted by Greek rho, right? That's usually that's the correlation coefficient that assumes a linear relationship. So correlation is a good measure of dependence when random variables are distributed as multivariate elliptical, for example, normal. And if the risks are independent, then we have zero correlation, although it's not the converse. Zero correlation does not imply independence. But the correlation can be problematic for non-elliptical distributions. And then we know that a key issue with the correlation is that it assumes a linear relationship, and oftentimes the relationship is not linear. And so we tend to use a broader term. And notice the aim is well placed here. I'm glad that they used the terminology here. Notice it's dependence. So dependence is a broader term and generally superior, right? Because dependence includes correlation, but includes the set of nonlinear relationships as well. So dependence is the broader term, and oftentimes it's just safer and superior to say dependence, because if we say correlation, we're implying that correlation coefficient and we're applying linear relationship. So what does a cupola do? Well, if f(x) of y is a joint distribution function with continuous marginals, so here we have these marginal or unconditional distributions. So these are the normal, or I shouldn't say normal, these are the, see, f of x equals to u and f of y equal to v. These are the marginal cumulative distribution functions that we're used to dealing with. We're dealing with single variable cumulative distribution functions here, but we have two of them. The cupola function is the glue that allows us to bind these together in a cupola function and characterize a joint distribution function, f of x, y. So the cupola enables us to construct a joint distribution function from the marginals in a way that takes into account the dependent structure of our random variables. We have, Dowd looks at some simple cupolas, independence, minimum, maximum, and then we have Gaussian cupola, T-cupola, a whole long list of possible, there's really no limitation to the cupola function that we can employ. In the spreadsheet, I've got an example of a Gaussian cupola, maybe a little mislabeling that a little bit, but not to worry for our purposes in 5D2, under an assumption of correlation equal to 0.3. So I make a correlation assumption and then produce a three-dimensional plot, really, right, of the bivariate distribution function. So more specifically or numerically, that's the cumulative. More numerically, that's the spreadsheet really simplifies. Notice there's a few tabs in the workbook, but a lot of that's just the complexity of the cupola function itself. It boils down to the output, and these vary, just a few simple cells here. We've got a y and a variable x and a variable y, and then we can input, as in yellow, 5% and 5%, right, to produce these. So you can see the 5% applies that normal cumulative distribution function that we're used to seeing. So here in just this one row, we have an example of that univariate marginal distribution. And then for variable y separately, we have an example of that univariate marginal distribution. Then given a correlation input, the cupola function works in the background, comes back to us and produces a joint or bivariate cumulative distribution function. See, the cupola was the glue that glued together our marginals and produced for us a joint distribution function. In this case, if we think of these as probability of default, if we have one bond with a probability of default of 5% and another bond with a probability of 5% and then some correlation assumption, we end up with a joint cumulative distribution function telling us that the probability that both of them will default, or symbolically here, the joint probability that variable x will be, less than some value and the variable y will be less than some value is going to be equal to 1.22%. How does tail dependence can be investigated using cupola? Tail independence is an important issue because extreme events are often related, and models that fail to accommodate their dependence can literally lead a firm to disaster. If marginal distributions are continuous, we can define a coefficient of upper tail dependence of x and y as the limit.